Thank you, everyone. Thank you, everyone, for joining us. My name is Sarah Spengeman. I'm the Deputy Director of Communications here at Energy Innovation. For those of you unfamiliar, Energy Innovation is a nonpartisan clean energy and climate policy think tank. Today, we have an excellent presentation prepared for you on assessing the viability of hydrogen proposals. And before we get started, I just wanted to go over a few logistics. First, everyone is on mute, but we do encourage you to ask questions. You should be able to see a Q&A box either at the top or at the bottom of your screen, depending on how you've set up your Zoom. And we ask that you use that box to enter your questions rather than the chat box, as that's the best way for our panelists to be able to view and see the questions that are asked. We also have a feature turned on that allows you to vote up questions. So this is a way to be really efficient with our question answering to make sure that those of you who have the same question, we answer those first. And we will also have time at the end to answer all of your questions. Please do feel free to put your questions in throughout the presentation, but we'll be sure to get to them at the end as well. This webinar is being recorded, and so we'll be happy to share the recording with you. And if you registered, you will receive the recording automatically. And so without further ado, I want to introduce our panelists. First up, we have Sarah Baldwin, who's our Director of Electrification Policy. Then we will have Hadley Talixon, who's a policy analyst on our electrification team. And then we will have Dan Esposito present, who is a senior policy analyst on the power sector transformation team. So I'm going to go ahead and turn it over to Sarah.
Great. Thanks, Sarah. And thank you all for joining us today. I really appreciate you taking some time to be with us and learn more about our recent research. So just a quick overview of our hour together today. We're going to do a quick background on hydrogen as well as the background on the report and the research that we conducted. We'll then turn it over to Hadley to talk about hydrogen and its implication in the building sector. And then Dan will talk about hydrogen and its implications in the power sector, as well as discuss some of our top line policy recommendations based on our research. And then we'll leave the last 15-20 minutes or so for Q&A. And just a reminder, please do use the Q&A feature as opposed to the chat, just so we make sure we capture as many of your questions as possible. Next slide, please. So before we dive into the research, I want to provide just a quick primer on hydrogen. While we're all hearing about it more and more these days, it may have been a minute since some of us took chemistry. So just a quick recap, hydrogen is the most abundant element in the universe. Hydrogen gas is colorless and odorless. It's also highly flammable. I put the famous Hindenburg blimp photo here on the right, which is what a lot of us tend to think about when we think of hydrogen. Certainly not the most ideal correlation, but it is a very flammable gas. So important to keep that in mind. Now, while it is scarce in the atmosphere on Earth, and there are no naturally occurring deposits, it therefore must be produced. And there are different methods of producing hydrogen, and each have different greenhouse gas and other emissions impacts. When burned, hydrogen emits mostly water, as well as various oxides of nitrogen or NOx. And when emitted into the atmosphere, as in if it is leaked into the atmosphere, hydrogen increases other greenhouse gases, resulting in indirect global warming. Next slide, please. So some of you may know this already, but 95% of the hydrogen produced today is what they call gray hydrogen, insofar as it is produced via a highly carbon intensive process. And that hydrogen is used in oil refining, about 60%, as well as ammonia production, about 30%, largely for agricultural purposes, but also other chemical feedstocks. Now I've got on the right here the three main categories of hydrogen. Many of you have probably seen the full rainbow of hydrogen out there, everything from turquoise to pink to purple to blue. But the focus of our report was really on these three core types of hydrogen for the sake of simplicity. But for those who want a little bit more background on some of the other types of hydrogen, you can definitely, we have a little call out box in the report that talks about the different methods of producing hydrogen. So gray, of course, as I discussed, is splitting natural gas or methane into hydrogen, and that also produces carbon dioxide, which is typically emitted into the atmosphere. Blue hydrogen is the same process, but if you can capture and store that carbon dioxide or reuse it in some way, then in theory, that is a means through which you can reduce or mitigate some of the carbon intensity of that blue hydrogen. That does not mitigate necessarily the upstream natural gas or methane emissions from the feedstock. And then finally, green hydrogen, which is splitting water into hydrogen through electrolysis. And it has to be powered by, this says water or wind, this is just a graphic, but any renewable resource, solar, wind, water, geothermal. And because the feedstock is renewable energy and it is emitting only the hydrogen and water and the resulting NOx, there's no carbon dioxide emitted. So this is the greenhouse gas free version of the three hydrogens here. And Ralph, I'm seeing some comments come in from you, and I just had a slide, actually just the one before that, that yes, hydrogen is very flammable. Next slide, please. So the impetus behind our research was really the fact that we're seeing more and more hydrogen pilot projects announced. Many of them are utility-led. This graphic here from S&P Global Market Intelligence shows that just from the third quarter of 2020 into the third quarter of 2021, a significant uptick in different proposals. And around a dozen or so states have these proposals, and they're growing in number. I'm sure this is now out of date, but upwards of close to 30 projects being proposed. Many of the proposals focus on blending hydrogen into existing natural gas infrastructure for use either in buildings or in power generation. And one example that has recently been approved is New Jersey Resources Corp is already blending 1% hydrogen in its service territory. And most of the proposals focus on green hydrogen, but not all. Definitely an array of applications. You want to go to the next slide. Just to drill down a little bit into some of the details of these various proposals. This is just a snapshot again from that same S&P Market Intelligence source, but they vary in terms of what they're trying to accomplish. I'll point out the third one down, Dominion Energy, because that's my gas utility here in Salt Lake City. And they have a 4-phase pilot project that they're aiming to achieve a 5% blend of hydrogen with natural gas in Utah's gas distribution system by the year 2030 to serve buildings. Others are looking at integrating the same sort of concept of blending into the distribution system. And then there are others that are not here, that are not shown here, that are looking at different industrial applications or transportation applications. So, but the vast majority of these utilities are definitely looking at the use of hydrogen in either power generation or the building sector. Next slide, please. And then finally, certainly added context to this conversation is the fact that the bipartisan infrastructure law that was recently passed includes upwards of $9.5 billion worth of funding to support clean hydrogen initiatives. Of that 9.5 billion, about 8 is devoted to creating regional hydrogen hubs. And there are different requirements for those hubs, including piloting hydrogen for use in buildings and in power. And of course, the Department of Energy also has a hydrogen office, and they are working a lot with the Office of Fuel Energy to figure out synergistic applications of hydrogen throughout the fossil fuel infrastructure. So to set the ground for our conversation today, there's a lot of movement and a lot of momentum around hydrogen. And while a lot of the impetus behind this is the notion that hydrogen, particularly green hydrogen, can create carbon-free solutions for, in particular, our utilities and our building sector, there are some legitimate concerns around what that means, both for consumer costs and safety risks, but also for air pollution and the viability of actually reducing emissions. So our hope is that this research can help utility regulators, state policymakers, stakeholders involved in these proceedings, and others really critically evaluate hydrogen proposals while exercising a bit more skepticism with respect to the viability of these pilots and programs, especially when they are ratepayer funded. So with that, I'm going to turn the time over to Hadley, and she's going to dive in.
Thank you, Sarah, for that introduction and background, and to just kind of encapsulate that into what motivated us to explore this topic is really understanding what merits does hydrogen have and where is it kind of an potentially overhyped because it has a lot of momentum, where is it viable, kind of making a distinction between the excitement with it and its feasibility. So Sarah, you can go to the next slide, please. Thank you. And to add a little bit more context and background with this momentum and enthusiasm around hydrogen, I wanted to touch on the piece around utility motivations for potential hydrogen investment projects. So firstly, it's important to note that the utility business model favors capital expenditures, and where they can spend money to upgrade or install infrastructure, they'll generate profits from those returns. And while they generally pass their fuel costs through to the customers, it's really the infrastructure investment pieces where they'll see a return on profit. And so with gas utility, with gas utilities, these may be particularly interested in hydrogen as it provides a pathway for them to maintain their current fuel delivery business model through a continued need for investment in their pipeline infrastructure from transmission and distribution pipelines. So on the left of this slide here, you can see a gas network system where you could have hydrogen blended into positions in the transmission pipeline, as well as the distribution pipeline for serving end uses for commercial and residential buildings. And on the right here is a map of the inter and intrastate transmission pipelines in the US. This represents around 300,000 miles of pipeline. And what's not shown on this map is the 2.5 million miles of gas distribution pipeline. So that pipeline serves gas distribution for arriving in buildings and homes. Comparatively, hydrogen has around 1,600 miles of dedicated pipeline, largely used for delivering hydrogen to industrial sectors for consumption. So if we're looking at the proposition of converting around 2.5 million miles of natural gas pipeline to fit the needs of hydrogen distribution, that would require a high level of investment and has opportunity for high returns on investment from those infrastructure investments. Next slide, please. So with that in mind, our report looked into the types of considerations that would impact hydrogen's viability for use in the building sector. And the first step we thought about was looking at the feasibility of integrating hydrogen into the pipeline system. And we'll touch on a couple of the key differences between natural gas and hydrogen that Sarah mentioned earlier, because those molecular differences are important in how hydrogen interacts with the pipeline system. And because of those differences, with the current system, blends in pipelines can really only maintain or fit within a blend limit of around 5 to 20% hydrogen after you conduct sufficient system-wide testing. So you're still looking at low blend levels of hydrogen in that system. And that's because a couple of different reasons around hydrogen as a molecule. It's a much smaller molecule than natural gas, and this can cause issues in steel pipelines, which most transmission pipelines are. Hydrogen molecules are so small that they can kind of move within the pipeline, the steel pipeline, and cause embrittlement, which can exacerbate cracks in pipelines. This causes risks around leakage, but also rupture from these cracks. And because hydrogen has a higher flammability range than natural gas, as Sarah mentioned earlier. It's capable of igniting, particularly when released at high pressure. And this is a problem with transmission pipelines because they move gas at high pressure and in large volumes. Distribution pipelines in the US, so those 2.5 million miles that I mentioned earlier, those are largely made of polyethylene plastic. So you don't have those same risks around cracks, but hydrogen can leak at rates much higher from plastic pipelines compared to methane leakage. And this can pose flammability risks if that hydrogen accumulates. This could happen in poorly ventilated areas or more densely populated areas. Though it is worth noting, hydrogen, because it's a lighter molecule, rises up from the ground faster. So in open areas, it's not as much of a concern, but it's when you have poorly ventilated areas or dense areas where hydrogen could accumulate. And these leaks also have an impact on climate warming. Hydrogen has a secondary warming effect due to the reactions it has in the atmosphere. And while it's not as potent as methane when you're looking at the same timescales for impacting climate warming, if you're looking at a shorter time frame, so on a 10-year timescale, the climate impacts from hydrogen can be pretty strong, and researchers are emphasizing a need to focus on leaks in distribution of hydrogen as an area of focus for mitigating short-term warming. And so as we're looking at reducing carbon emissions at high levels, particularly in the near term, release of leaks from hydrogen have particular impacts around climate there that can be counter to other emissions reductions efforts. And then to round out the discussion of looking at pipelines, going from transmission to distribution to now looking at pipelines in homes, in buildings, those would also need to be considered as they're capable to handle hydrogen due to risks around flammability and leakage. And this image on the right is a map of located methane leaks from gas distribution pipelines in Boston. So this kind of gives you a sense of where high levels of leakage are already occurring with methane, and that can be expected to be exacerbated with hydrogen. Though this is, Boston does have an area that's more prone to leakage due to its older pipeline infrastructure. But this map comes from a partnership between EDF and Google Earth. So before even a small amount of hydrogen can be blended into pipelines, you need significant testing across all stages of the distribution, transmission, and pipelines in buildings. And there are many regional differences across all of these pipelines, so you need very localized testing as well. And that's before you can even support these low-level blends of around 5 to 20%. Next slide, please. Then when you're looking at hydrogen for use in appliances, then you have additional considerations that are similar to some of the concerns around flammability and leakage that you have in the pipeline system, but you also have additional health risks from using the fuel, particularly around nitrous oxides or NOx emissions. In gas appliances, hydrogen poses a risk of flame flashback, where an ignited flame can travel back down into the pipeline, and this can cause explosion risks. Hydrogen also burns much faster, correspondingly hotter, and because of this, it also produces more nitrous oxide or NOx emissions when you're burning hydrogen compared to natural gas. NOx is a pollutant that can cause breathing problems, and its emissions from current natural gas stoves has been shown and tied to increased rates of asthma. So it's a damaging pollutant, and hydrogen has the potential to exacerbate that problem. And if we're looking at the comparison of how much NOx emissions come from hydrogen versus natural gas, while there aren't a high number of studies really around this problem in the building sector and looking at residential or commercial appliances, in industrial settings, blends of hydrogen for combustion, if we're looking at a 25% blend of hydrogen, that has been shown to increase NOx emissions by almost double. And if you're looking at a 100% combustion of hydrogen, that has shown to lead up to 6 times the amount of NOx emissions compared to burning methane alone or natural gas alone. And while that is in an industrial setting, if we're looking at a similar scale of magnitude at the appliance level, this will really exacerbate a lot of the problems around natural gas NOx emissions already in homes. And in California, to give a sense of the scale of the problem, this NOx pollution from burning natural gas in homes is almost 7 times higher than the NOx emissions from burning natural gas for power plant and energy generation. So without technology to mitigate this on the appliance level, this would have an impact in homes and communities. So if we're looking at all of these technical compatibility factors with existing gas appliances and hydrogen related to flammability and flame speed, there also are blend limits that appliances impose on how much hydrogen they can accommodate. So they also impose around a 20% blend limit. And even if all of the pipeline infrastructure was built out and upgraded to support higher hydrogen blends, the appliances themselves couldn't handle much more than 20%. And even with the scenario in which you can blend higher amounts of hydrogen for use in appliances, you'd still have concerns around leaks. And another important factor to note there is, as you increase the amount of hydrogen, the issue of not having an odorant that's compatible with hydrogen becomes more prominent, and you couldn't detect leaks via odor as we can with natural gas to alert us if there's a leak in our stove or something like that. So if we look at combining all these factors across pipelines and appliances, the current gas grid system can support at most low hydrogen blends, the highest being around 20%. And to achieve any blending amount, significant system-wide testing of pipeline materials and connectors and appliances is needed. Next slide, please. And if we look at where that 20% maximum blending limit gets us in terms of emissions reductions, we really only get around 6 to 7% carbon emissions reductions from combustion. And that's because hydrogen has a lower energy density per volume. So a 20% blend of hydrogen corresponds to around 6 to 7% energy content, and thus only reduces emissions by that same amount, 6 to 7%. And if we wanted to move beyond these low blend limits to achieve higher carbon emissions reductions, the entire natural gas system that delivers fuel and uses it in buildings would need to be replaced, all with hydrogen compatible materials and equipment. In terms of appliances, if there are appliances that are capable of handling higher hydrogen amounts, the replacement would need to be figured out across a whole distribution region for a gas region in order for them to begin distributing hydrogen. And if you miss an appliance replacement, that and you're left with only 1 or 2 appliances that can't handle these high hydrogen blends, you could risk explosion. So really having that replacement of appliance piece figured out will be important in considering whether or not this is possible. And if in the scenario that all hydrogen appliances would be installed properly, they still have efficiency penalties around how they are able to use energy. And so because we're talking about green hydrogen, which takes renewable electricity and converts that into hydrogen, which would then be distributed and consumed in homes, you face efficiency losses along the way, first with the electrolysis to convert the electricity to hydrogen, and then even assuming high best-in-class natural gas furnace efficiency level based on what's on the market today, if you assume that for hydrogen furnaces, you still see a lower overall efficiency compared to other zero carbon appliances such as electric heat pumps and electric induction stoves. These all have efficiency advantages over the potential for hydrogen appliances. With heat pumps, you see around 3 to 6 times more efficiency there compared to hydrogen furnaces, and induction stoves compared to hydrogen stoves would also have around 3 times more efficiency. And the important thing to know about this efficiency is it also corresponds to the amount of renewable energy that you would need to have the capacity for to support this energy consumption. So comparing to direct electrification, with renewable electricity, you would need up to 6 times as much renewable energy capacity to meet the hydrogen heating demands in buildings. And on top of all these infrastructure costs to upgrade the pipelines, on top of appliance costs that could land in consumers' laps to replace all those, you're also looking at a fuel that itself is very expensive. It's currently 6 to 14 times more expensive in the US. So you're kind of seeing this high list of costs that can really add up for consumers. And with all that being said, green hydrogen kind of comes out as an inefficient and costly path to building decarbonization, but there are alternative pathways that can avoid these disadvantages and provide more efficiency advantages. Next slide, please.
Hey, Hadley, I think we've got to wrap up this section to leave time for the next one. So just heads up on that.
Okay, thank you. Do I have a minute to go through the electrification? Okay.
Yep.
Thank you. So electrification with electric appliances, as I mentioned, have high efficiency. They also don't have risks around flammability or NOx emissions, and they are available on the market today, which is not the case with hydrogen appliances. So you can have incremental replacements of appliances for electric as an appliance needs to be replaced, and you don't have to have this network-wide whole replacement of appliances the way you would with hydrogen. So in summary, electrification offers much higher emissions reductions potential, much faster while using less energy overall. And hydrogen in buildings has health risks around cost, safety, and health that only increase as you blend higher amounts. So with that, I'll turn it over to Dan to talk about hydrogen in the power sector.
Thank you, Hadley. And next slide, Sarah. Thank you. So good afternoon, everyone. I'll be talking about the challenges and opportunities that come with using hydrogen in the power sector. So several utilities are proposing to blend hydrogen with natural gas to feed into their gas-fired power generators, with the goal of gradually increasing that share of hydrogen on a path to only burning hydrogen. Some utilities and independent developers are also proposing to build new hydrogen-ready natural gas power plants. Though as of now, burning hydrogen for power faces some serious technical and safety challenges. So hydrogen-fired turbines aren't yet commercially available, and the prospect of retrofitting natural gas power plants to run on hydrogen might not ultimately be feasible. Hydrogen blending for power generation faces many of the same types of challenges as it does for use in buildings due to its different chemical properties. For example, hydrogen's lower volumetric energy density means you need to deliver much more fuel for the same power output. In total, retrofitting existing turbines to accept more hydrogen might require replacements and additions for larger fuel delivery systems, new materials that are less susceptible to embrittlement, tighter seals, systems capable of reducing flashback risk, improved ventilation, and hydrogen gas detection systems. Meanwhile, blending might do little to reduce greenhouse gas emissions while worsening local air pollution. For example, a 50% hydrogen blend would only cut carbon dioxide emissions by about 22%, but it would increase NOx emissions by about 35%. And turbine manufacturers are exploring new technologies to limit NOx emissions from burning hydrogen, but they haven't found success yet, with one study from a manufacturer conceding that, quotes, some flexibility might be needed on NOx limits in the future, unquote, if hydrogen is to play a role in the power sector. However, we shouldn't be sacrificing communities near power plants that are already disproportionately burdened by such pollution. So if anything, NOx emissions limits are likely to tighten in the future. So hydrogen blending does little for climate, and new natural gas power plants being proposed on the potential of eventually transitioning to burn pure hydrogen risk being stranded if manufacturers can't figure out how to solve hydrogen's many challenges. We're already seeing this reasoning showing up in the regulatory record, with the New York Department of Environmental Conservation citing many of these technical issues as part of its grounds for denying an air permit to the Dan Scammer Energy Center, which is a proposed natural gas power plant whose application had cited the possibility of eventually transitioning to burning hydrogen. Okay, yeah. Another important issue here is that green hydrogen won't be competitive in the power sector until the grid needs long duration energy storage services. And even then, the jury isn't out on which technologies might be best suited to provide these services. Natural gas power plants are often competitive as a baseload resource capable of running around the clock, and for intraday balancing, meaning they can ramp up to serve high demand periods and then ramp down. Electrolyzing hydrogen and then burning it for power will never make sense in these rules, as these processes lose all but about 18 to 46% of the initial clean electricity, depending on things like whether you have to store the fuel. Instead, you can just directly use clean electricity in most hours and use lithium-ion batteries, which have a much better round-trip efficiency of about 80% to fill in those intraday gaps. Green hydrogen's value lies in being able to store much larger amounts of energy for much longer periods of time than today's battery technologies, such as by, such as by storing hydrogen in underground salt domes or converting it to liquid ammonia for above ground container storage. When using this capability, the poor economics of its low round trip efficiency can be overcome. What this might look like in practice is you electrolyze a ton of hydrogen in parts of the year when we have lots of extra renewable generation, store it for months at a time, and then draw from it in the winter doldrums when there's comparatively much less solar available. From a wide range of studies looking at high penetrations of renewable energy in the US, we might not need these long duration storage services until we reach 80 to 90% clean electricity in the US. And since we're a long ways off from this, the main focus for power sector decarbonization should be on building as much wind, solar, and battery storage as possible. In the meantime, we absolutely should be researching and demonstrating lots of potential long duration storage technologies, including green hydrogen. However, since blending has such little value, and since today's natural gas power plants are built to serve needs that differ from green hydrogen's value proposition, it makes more sense to test turbines that can safely burn 100% pure hydrogen with these low NOx emission rates that have been out of reach. If developers can solve these challenges, then it might pencil out to start retrofitting today's natural gas equipment to transport and burn pure hydrogen. It should be mentioned, though, that hydrogen isn't the only technology that can serve long duration energy storage needs. Other technologies like iron air batteries, advanced compressed air energy storage, and even potentially gravity energy storage systems all claim to have potential higher efficiencies, fewer geographic constraints, and less pollution compared to hydrogen. A nuclear and geothermal renaissance in the US could also reduce the need for long duration energy storage services if you have more clean, firm power. Hydrogen's unique advantage is that the fuel can be used in other sectors, so the presence of other markets might drive down its costs more than these other technologies. But in any case, the winning long duration energy storage technologies won't be known or have a market for their services for many years. Next slide, please. So far, we've been talking about burning green hydrogen, but you can also run hydrogen through a fuel cell, which generates power with only water as a byproduct with no NOx emissions. It's essentially an electrolyzer in reverse. Fuel cells have been around for a long time. They're great in smaller scale applications as they're clean, they're quiet, modular, and all of this allows them to be sited where you wouldn't want to put a power plant. After a certain size, the brute force method of just burning hydrogen for power becomes more competitive with today's technologies and supply chains. But it is possible that the fuel cells could become cheaper and someday be used for utility scale power. In the meantime, though, their best use case will likely be in providing backup power to microgrids and critical facilities like hospitals. And this shores up their reliability and cuts down on the use of diesel generators that we use today. While there might be narrow opportunities to build hydrogen capable pipelines to serve fuel cells on key circuits or at these critical facilities, even these applications might best be served by delivering compressed or liquefied hydrogen by truck for occasional, likely infrequent resupply. In any case, the potential benefit of maintaining a few dedicated hydrogen pipelines for this purpose shouldn't serve as grounds for utilities to blend hydrogen with natural gas or otherwise look to upgrade the rest of their distribution networks. Next slide, please. So to wrap up, our research led us to 4 recommendations to help policymakers assess the risks and opportunities of hydrogen. First, utility regulators should exercise skepticism when considering ratepayer-funded proposals to blend hydrogen with natural gas for distribution in pipelines or use in power plants, and they should put a high burden of proof on utilities to demonstrate viability. Any plans to blend hydrogen or invest in hydrogen-ready infrastructure should demonstrate a clear, long-term strategy to achieve full decarbonization and show why hydrogen would be better suited to a given use case than competing options like electrification. These requirements should hold even if current legislation requires less than full decarbonization, as ratepayers, frankly, face a lot of risk if utility investments that are made to meet near-term emissions reduction goals have to be abandoned for other strategies if or when legislators mandate full economy-wide decarbonization. Second, where ratepayer-funded pilot projects are already underway, regulators should define clear goals and outcomes, as well as metrics for assessing utility learning with specific relevance to the utility's jurisdiction. However, more general research is better suited for the federal government and private investors. For example, the US Department of Energy can better manage higher risk technological research and development studies that have scalable impacts on utilities across the country rather than just one specific utility. This prevents local utility customers from being saddled with costs of nationally relevant and risky research. Third, regulators should look to proven, least regrets alternatives to hydrogen that allow electric and gas utilities and states meet their decarbonization targets. Plans that support the deployment of renewables and storage, the identification and sealing of methane leaks in pipelines, and building electrification, efficiency, and installation all pose much lower stranded asset risks than green hydrogen. For example, investments to weatherize homes and install electric heat pumps provably reduce greenhouse gas emissions and can be made incrementally over time, relying on existing electric transmission and distribution networks. And finally, state policymakers should explore using green hydrogen in the hardest to decarbonize sectors of the economy, such as industrial feedstocks, aviation, and marine shipping. For example, there is currently no substitute for hydrogen to produce ammonia for use in chemical fertilizer, and green hydrogen could take the place of about 2 million metric tons of highly polluting gray hydrogen used annually in the US for this process. Marine shipping and aviation might also benefit from hydrogen, which can be used as an input to more energy-dense fuels like ammonia and methanol, where today's battery technologies aren't energy dense enough to economically support longer, especially international trips. However, these use cases all have such high energy demands that it might make more sense to transmit renewable electricity directly to industrial sites and ports, where they can then electrolyze green hydrogen where it's used, rather than build new pipeline infrastructure to move green hydrogen across the country. So ultimately, utilities' roles in a green hydrogen economy might be to supply clean electricity to green hydrogen producers for use in these hard to decarbonize sectors, rather than be the producers and transporters themselves. There might be some mutually beneficial relationships here too, where, say, an electric utility could offer special rates to ammonia producers to electrolyze green hydrogen from renewable energy, which would help utilities integrate more renewables on the grid at a lower cost to ratepayers, while also offering cheaper fuel to industrial customers. Next slide, please. And with that, we want to thank you all for attending today, and we look forward to answering any questions through the rest of this hour or half hour.
Thank you so much, Dan. Thank you, Sarah. Thank you, Hadley. We do have some really great questions coming in. The first question is from Olivia, and she would like to know, do these utility proposals contemplate eventual blending concentrations greater than 20%? And if not, then what are utilities saying is the long-term point of green hydrogen blending, especially in the context of decarbonization goals where 6 to 7% reductions in GHG emissions is clearly not enough?
I can jump in there and say that, firstly, one of the issues that we're seeing with these proposals is they don't have a long-term vision mapped out super clearly in all cases when they're looking at hydrogen blending. And so when you're looking at these lower limits and testing what the distribution system can handle. It gets a little bit nebulous in the next stages, like, well, we could ramp up hydrogen beyond once we upgrade pipelines, or we could also incorporate renewable natural gas from biomass sources, but it's not really as clearly articulated as would make sense to begin this high cost and high time investment project to look at these low level of hydrogen blends, only to have an unclear vision on what that actually looks like in the end game.
And I'll jump in with just one other comment there, Hadley. If you look at that S&P list, and certainly encourage folks to go take a closer look at that, some of the proposals we're seeing also are really far out into the future, like, for example, the Dominion example I gave, which is aiming for not more than 5% by the year 2030. And I think, given the IPCC reports that came out last week, articulating the need for us to double down and ramp up on our climate mitigation efforts, I think that those 2030 timelines are candidly too little, too late.
Thanks, Sarah. Here is a bit of a technical question. Why does hydrogen leak in plastic pipes? Is it a function of the polymer structure, or perhaps less secure seals between pipe sections?
I can jump in here, and that's a really great question. I appreciate a technical question. Well, firstly, I'll say with looking at leakage from connectors, you experience leakage from those connectors also in the steel transmission pipeline system, as well as the connectors in the distribution pipelines. But if you're looking at plastic material specifically compared to steel, I'm not sure the specifics, but it is more prone to leakage. Like, the hydrogen can move more quickly through that material compared to steel, and that's what allows for that leakage.
All right, not sure what quite happened. There we go. Let's see. 1 second.
While Sarah is getting the screen share down, I can go to the next question. So we had a couple of questions around this topic, so I'm going to hopefully encapsulate them in a single question. What's the maximum amount of hydrogen on a percentage basis that you can blend with fossil gas without adversely impacting indoor air quality? And there was another corollary question that asked the question of, is it really worse than burning gas in building? So Hadley, I don't know if you know that.
Yeah, so if we're looking around the considerations around NOx emissions, firstly, because part of the inherent nature of hydrogen is that burn speed that you can only really mitigate if you're also reducing output, you're always going to have higher NOx emissions associated with hydrogen if you're burning at that higher rate, as the fuel is prone to do. In industrial settings that use combustion already, there are technical capabilities to limit NOx emissions, like selective catalytic reduction. And so in industrial settings, you have a little bit more control over what those NOx emissions outputs can look like, but you would still need technical upgrades or changes to handle hydrogen specific fuel, and research around what those upgrades specifically would be are occurring, but there isn't really a solid base yet there, except for looking at reducing that flame speed, and so reducing overall fuel output. At the appliance level, I'm not sure where it stands on those technical capabilities to look at NOx emissions specifically from hydrogen. I'm guessing there could be some similar capability as could happen at the industrial level, but you would need you would need different types of specificities with appliances to limit those NOx emissions. And in terms of looking at what blend limits could still be safe, I think the question really is, are the current NOx emissions from natural gas considered safe? And I would argue that they are not, particularly because many gas appliances are operated in poorly ventilated homes, and ventilated pollution is just emitted outdoors where it affects communities. So adding any amount of additional NOx pollution to that only exacerbates the problems that are already present.
Thank you, Hadley. Another question from Carl. Did you assess the plausibility of using pure hydrogen in these pipelines in the future? Obviously, in not so long, we need much more than 10% or 20% reduction in methane combustion.
Sorry, this question is considering the feasibility around blending beyond that 20% and what the upgrades would be needed.
Yeah, it says, did you assess the possibility of using pure hydrogen? So pure hydrogen in these pipelines in the future?
Yeah, so I think that kind of goes back to a lot of the issues that occur once you reach higher blend limits. It's really the presence of hydrogen, not so much the mixture between natural gas and hydrogen. It's not those mixing interactions, it's just the presence of hydrogen. And as you reach higher blend limits, you have the same issues as you would have in a 100% pure hydrogen scenario in that same infrastructure. And so if you were to achieve a 100% hydrogen fuel, that would require likely a replacement of all the materials of the existing pipelines, replacements of existing gas appliances. So you see the same kind of challenges as you do in a high blend scenario. And there, as I mentioned earlier in the presentation, there are pipelines that are dedicated specifically to hydrogen, but those are the 1,600 miles that serve industrial customers. And so because those needs were met through specific hydrogen pipelines, it's likely that that same kind of level of replacement and rebuilding of the pipeline specific for 100% hydrogen would be necessary if you wanted to move pure hydrogen.
Yeah, and I think one thing that's particularly enlightening is the appliance challenge, which is if appliances can only handle, say, maybe 20% hydrogen blend, and you can't go above that, then it doesn't matter what you do to the pipelines. You can't put in more than 20% hydrogen until you replace every single appliance and piece of equipment that burns or that draws gas from that distribution system. And it's a uniquely hard challenge. I think there's a lot of experimentation out there about designing household appliances that can burn pure hydrogen, but you need to design appliances that can burn any blend of natural gas and hydrogen, from basically pure natural gas, or at least 80% natural gas, all the way to 100% hydrogen. And if you can't design appliances that can burn any combination, then you'll be stuck in a situation where when you're trying to make this transition above 20% blending in your pipeline system, you change out a homeowner's appliances to burn hydrogen, and then say it takes 5 or 10 years to switch over every appliance, then they are sitting with useless appliances that they can't operate for that entire time period. And designing household appliances that can burn any blend is a much tougher problem because the gases are so different. So it might be possible, but because you're working with two different systems, it's expected to be quite a bit more expensive if it is doable, and probably clunkier as well to be able to manage things like the NOx emissions from the higher flame temperature.
And just adding on to that consideration around appliances, in terms of the most advanced that I am aware of, there's a prototype of one house, I believe, in the UK that is running a prototype test of 100% hydrogen and prototype appliances in that house. But that's a pretty limited operation compared to the market availability of electric appliances today. There's already a much more mature and larger momentum market there. So going from those kind of prototype levels to market has time delays as well. And I believe in terms of what the blending percentages are today that are the most advanced, I think the most advanced that I'm aware of is one operation in the US that is blending 1% currently. So that kind of gives you a range of where we're seeing the
Great. Thank you, Hadley and Dan. We've got a couple of questions now about what's going on in Utah. So Seth would like to know, if no combustion turbines are yet available to burn 100% hydrogen, how does a project like Intermountain in Utah expect to follow a path from 30 or less to 100%? Will they have to swap out turbines or turbine combustion elements for every incremental step to higher H2 content?
Yeah, happy to take this one. And I don't want to claim to know everything that Intermountain has behind the scenes and where they are specifically. But Intermountain, for those who don't know, used to be a large coal facility that provides power, I think, predominantly to LA via dedicated transmission. And they're, I think, in the process of switching to natural gas with the ability to eventually burn more green hydrogen over time, with the ultimate goal of 100% green hydrogen. So they are kind of doing this in parallel with equipment and turbine manufacturer research on hydrogen blending and being able to burn pure hydrogen. So I'm not sure that they have a certainty of how they're going to get there. What I would expect a plan like this to look like would be, as you're retrofitting to burn gas, you're probably accounting for some known variables, like if hydrogen is less energy dense and requires more throughput, you would probably want to put in larger pipes from the start, and probably have, more appropriate materials in the plant and everything to eventually make the switch to hydrogen. But I'm not sure that there's like a certain pathway. An interesting kind of unique thing about Intermountain that's different from a lot of these other power plant proposals predicated on burning green hydrogen someday is that Intermountain is relatively remote, and it's around a lot of salt domes that are kind of natural places to store large volumes of green hydrogen. And it has decent renewable resources in the region as well. So it kind of has a unique circumstance where you can probably generate a lot of renewable electricity, use that to electrolyze green hydrogen, store that in the salt domes, and then draw from it either for blending or eventually for full operations someday. I am not sure what research has been done on NOx emissions and, are they meeting EPA limits? Are there communities nearby that might suffer the effects, or is it sufficiently remote enough where it's maybe less of an issue? There's still lots of open questions, but that's kind of where things stand now with that project.
And Dan, there's another question about the Intermountain Power Plant. This one is from Josh, and they're asking, thinking about the plan to convert the plant to a hydrogen natural gas blend, how will the electrolyzer discharge the power? Does it go back through a turbine or directly into the transmission system to serve load?
I'm a little bit confused by the question, so I apologize if I'm not answering it quite right, but my understanding is you electrolyze the green hydrogen from clean electricity and water, and then you have those molecules which you're storing underground, unless there's not really a use case in which you would just burn it right away, because you're taking power to make it and then running it through a turbine, so you would just be dealing with a pretty big efficiency loss there. Yeah, so you would store it and then you would burn it in the turbine to generate electricity rather than running it back through an electrolyzer. Unless you're talking about fuel cells, which are not the same exact technology and not part of Intermountain, the Intermountain project, to my knowledge. But that would be a different thing where you can store that green hydrogen, then run it through a fuel cell, which generates electricity, which you can then send onto the grid or serve your microgrid or critical facility needs.
Thanks, Dan. And Josh, do feel free to follow up over email if that didn't get at the question you were asking, if I misunderstood it. And let's see, great question from Thomas. Given all of these problems, what do you think is motivating utilities to undertake hydrogen demos? Who would like to take that one?
I can jump in. I think, in the case of most regulated utilities that have shareholder investors, clearly the motivation is to, continue to remain relevant in a carbon constrained future, knowing that natural gas has still a huge greenhouse gas impact, and we have to reduce natural gas writ large across all sectors in order to achieve a 1.5 degree scenario in a stable climate. So the idea behind hydrogen blending with gas certainly is motivated, I think, in part by the climate intent, but more so, I think it's that capital expenditures on pipelines and gas power plants are what earn returns for shareholders. And that is strongly motivating for most utilities. And also, I think there's a lot of existing infrastructure that folks are seeking to continue to utilize because they have not yet reached their useful life. So there are a number of motivating factors at play.
Thanks, Sarah. One last question. Doug has asked, does EI see any near-term use cases for hydrogen today?
I would say the clearest cut near-term use case is where gray hydrogen is already being used today. I mean, a lot of it is being used for oil refining, but there's a certain sector of ammonia production for use in fertilizer that probably will not be going away. So if there are partnerships there where you can get some cheap green hydrogen, maybe electrolyzed from when we have a lot of renewable energy to the point where we would otherwise curtail it, and then entering into partnerships with ammonia producers who are large consumers of hydrogen and concentrated in certain parts of the country. That's an immediate one. Where gray hydrogen it's especially polluting because you have an input stream of natural gas where you're generating this or producing this gray hydrogen, but then you're burning natural gas to generate the heat to split that hydrogen or the hydrogen from natural gas or methane molecules. So it's highly polluting, more so than one stream of natural gas by itself. And so swapping one fuel out for the other, chemically identical, but coming with very different greenhouse gas emissions implications. There's a clear climate win and probably a clear market for it if it could be produced cheaply enough.
Okay, well, thank you so much, Hadley, Sarah, Dan. Like I said, this webinar was recorded and you'll get a recording of that. I also wanted to direct you to a link that was put in the chat to sign up for our trending topics email list, which would make sure that you get the latest research. You're invited to our upcoming webinars and events. And we thank you, everybody, for joining. If your question didn't get answered, do feel free to reach out. So thank you so much.
Thank you all.